Hi, my name is Thales Castro and I'm a master's student at the Federal University of Pernambuco. The goal of this presentation is to talk about the fabrication process and characterization of a fiber optic refractive index sensor with a D-shaped plastic optical fiber. This research is advised by Professor Joaquim Martins from the Photonics Group Sensors and Instrumentation Lab. The presentation is structured in 5 sections: the sensor working principle, the methodology used in fabrication and characterization, the measurements performed in different mediums, conclusions about the sensor characterization, and acknowledgements. The sensor fabrication process is closely linked to its operating principle. The optical fiber used in the construction of the sensor is plastic and its core has a diameter of 0.98 mm. The cladding surround this core is 0.02 mm thick. The confinement of the guided optical signal in this fiber depends on the difference between the refractive index values of the core and the cladding. This dependence decays as we move away from the core cladding interface and, therefore, variations in the medium outside the cladding do not significantly influence the optical power magnitude. To make the sensor capable of detecting these variations, the cladding is removed and the optical power of the guided lights starts to vary more significantly in relation to variations in the refractive index of the external medium. As the confinement of light in optical fiber is due to the phenomenon of total internal reflections, it's important to delimit the operating range of the sensor so that there are no major loss in optical power and the compromise of the sensitivity. Removing the cladding from the optical fiber results in the structure known as the D-shaped. It gets its name from the shape of the cross-sections. This cladding removal process can be performed in different ways, but the methodology adopted was the removal by polishing because it's a simple process. As for the instrumentation and methodology used in fabrication of the D-shaped optical fiber, as the technique chosen for the fabrication of the D-shaped was a mechanical polishing, it was necessary to fix the optical fiber on some type of support in order to increase the mechanical resistance of the polished region and facilitate the handling during measurements. The support used was an acrylic substrate and epoxy resin was used for fixation. The polishing takes place by the contact of the optical fiber fixed on the substrate with abrasive discs kept in rotation at constant speed. Each disc has a different levels of roughness, allowing control of the speed of removal of the optical fiber cladding. This contact is managed by a nanometric step motor that moves the optical fiber closer or farther away from the disc through the actuation of a control system. The control system used consists of a photodetector circuit, an amplifier stage, a capacitive filter, and the microcontroller system responsible for the logical treatment of the measurements. For sending and receiving the signal, a light source is used, which is a 650 nanometer light emitting diode, LED, and a photodetector circuit composed of a photodiode coupled to a preamplification stage. Basically, the control system measures the level of the optical power that reaches the photodetector and manages the function of the motor so that it can continue or not with the polishing process. The desired optical power level is pre-configured by the user. In addition to managing the step motor operation by means of previous user configuration, the control system also allows monitoring the variation in optical power during the entire polishing process. This measurement can be used to optimize the fabrication process and evaluate the effect of adding roughness to the polished surface. At the end of the polishing process, the first tests are carried out to qualitatively evaluate the sensor response. In the graph, this capacity is represented by the vertical distance between the peaks or each of the substances. After the tests, the sensor is ready to perform the measurements and its characterization begins. The first parameter calculated to characterize the sensor is the depth reached in the polishing. According to this mathematical modeling, to calculate this parameter, we only need to define the width of the polished region, because the radius of the optical fiber is already known. From there, optical microscopy is used to obtain images of the polished region, and through software, this width is determined. The value found was 850 micrometers, which results, according to the model already present, in a depth of 236.61 micrometers. Once the depth reached with the polishing is known, measurements are carried out in different mediums. The mediums usually rare is distilled water, acetone, isopropyl alcohol, and glycerin solutions with different concentrations. The measurements are displayed on this graph along with the linear feet represented by the red line. Through this graph, it's possible to observe that the sensor can be used in both in the identification of substance and in the measurements of concentrations, which open up a huge range of possibilities. Finally, from the measurements, it's possible to calculate the sensitivity and the resolution of the sensor. This table makes a direct comparison between the produced sensor and two other similar devices found in the literature. Through it, it's possible to observe that the sensor has a high sensitivity even in a wide measurement range. From the values in the table shown above, it's possible to observe that the sensor has the highest sensitivity among two similar devices found in the literature. Another important point observed from the measurement is the sensor has the potential to be used in measurements of concentration, characterization of mixtures, detection of leaks or contaminations. Finally, on behalf of our authors, I would like to thank the Federal University of Pernambuco, and specifically the postgraduate program in electrical engineering, responsible for all the infrastructure used in making the sensor. I would like to thank to the Brazilian National Agency for Petroleum, Natural Gas and Biofuels, ANP, which through the Human Resources Program provide parts of the resources used. Thank you.